what I want to talk about today is how we actually build our Go web app and how we make it testable. But what I really want to do is start a discussion about like the better way to test Go web applications. When we were designing our app and how to test it, there were not a lot of good examples out there. And I know that you all are some of the people who push testing forward. You do testing better than anybody else. So I want to show you what we do, and I hope that some of you can take that, criticize it, and move the Go community forward in the way that testing is done with web apps. So that's the goal. So there's a lot of primary source stuff taken from our code base. So first, just to give you context, I want to show you what Sourcegraph is. It's a code search engine, and we actually semantically analyze code. That means we don't just look at the text. We run it through a compiler. We understand what every single token in the text of the source code does. And that means we can show you usage examples. Everybody else who uses a function or a package everywhere else on the web, on GitHub. And you can search by function name. You can see who else around the world is using your code, people from all around the world. And it's a really rewarding feeling. But the reason why we created it is because we hate writing code that we know someone's already written. We just want to be more productive and not reinvent the wheel. So I would hope that it's useful for all of you. I'd love it if you checked it out and sent us feedback. And I just want to show you what it looks like real quick. So here's sourcegraph.com. I can just start typing, if I don't make typos. And there's just all the functions named new request in HTTP. I can pull it up. And here it takes me to the code. Over on the left is the definition of new request in the Go standard library. Over on the right is the docs, usage examples, some other information. And then in this view, you can actually put your mouse over anything and just get a real quick doc string. You can also drill into all the usage examples. You want to make a request. You want to make a post request with a request body. So how do you do that? And here's someone who's passing in a buff. You can dig into any of these. So this helps us do our job a lot quicker, and I hope that it'll help all of you. We also have a repository page, so similar to GitHub in that way. So that's Sourcegraph. There's a lot of stuff that goes into it. We have a large web app, and we have a large backend that actually does the analysis. And virtually all of this is open source. What we want to really do is make every programmer more productive. So I'm not going to talk about the backend and language analysis. I want to talk about the web app and how we test that. And here's what our web app looks like. So it's 3 layers. We have the web front end, which is what you see in the browser. And that, whenever you go to any page in the web front end, that will make a request to our API. So we dog food our own API in that way. And then our API will make a request to the data store, which is the thing that actually issues the SQL and gets the results back in the database in the rows. And then data store passes it to the API. The API sends back the JSON to the front end, just like a normal API client relationship, and then the front end will render that in a template. By the way, if anyone has any questions while I'm talking about this, please interrupt me. Just raise your hand, and question askers get T-shirts. Any questions so far? That's not a valid question. Yep. The API, there's some people who, what's that? Oh yeah. The question was, is our API open to the public? We're kind of in the middle of doing that right now. Our API client is open source, so everything that I talk about here, you can go and see the actual source code. We have not done all the work around authorization and rate limiting and tokens for API. So anyone who wants to use it is just like coming to us, and we're giving them a little secret to use, but we're going to release it really soon. As I said, we are a small team, and yeah, we can't do everything. Yeah, the question is, what languages can you search on Sourcegraph? And right now we have support for Go, Ruby, Python, JavaScript. Go is easy, it's statically typed. The other ones are a lot harder. We have to perform type inference, and they're not perfect, but they're pretty good. So if you use any of those languages, try Sourcegraph out. All right. One more question? The question was, why did we write it in Go? There's kind of a weird reason. Go makes it super easy to analyze its own source code. So when we were prototyping Sourcegraph, that's what we were optimizing on. How quickly can we write something that analyzes any kind of source code? And it turns out we still love using Go, and we make the choice to write in Go every single day because it keeps our code really simple. It's statically typed. It's really easy to refactor, and it is very simple. I know that some of you are switching to Go. You probably have some of the same reasons. There are some pains that we've experienced with Go, but overall we like it a lot. All right. So yeah, this is our web app. And before we go into how we have built tests in that web app, I want to talk about what we had before so that I can show some of the challenges that people who are testing web apps now in Go face. So the way our tests used to work is, the V0 for every kind of test. You actually connect to the database, you put fixtures in the database, and that's slow. And then you'll actually issue an HTTP request to your API. That API call will go and hit the database. You're basically not doing a unit test. You're like hitting the actual API as it exists. Then your test code will parse the response body and check against the expected. And so it's pretty messy. And here's what, if you go to any tutorial that says how do you test HTTP handlers in Go, this is what it'll tell you. For those of you who don't use Go, I'll just run through this again. So the fixtures are up here. And then we connect to the database. We set up the API server so that we can access it. In a transaction, we insert the data in the database. We make a request. We parse the JSON, which is down there. And then deep equal, is it equal to what we expected? So there's a lot of boilerplate code. There are actually a lot of problems with this. So as I said, it's slow because we have to actually hit the database. And if we don't just hit the database but hit some other external service, it becomes even slower, which is not good. It's hard to refactor because there's a lot of behavior that we program over and over again. And for example, the strings for the URLs up here, those are specified as strings here. So if we change the URL structure, then it's not easy to automatically refactor those and see what breaks. So they don't help us in refactoring, which is a big reason why we like tests in the first place. And there's a lot of messy boilerplate code. For every test, we have this whole series of code of lines. And sometimes we want to do things that are slightly different. We actually had a lot of bugs in our testing code, which was not fun. But this kind of testing did suffice for a little bit. But as we grew, some of the requirements changed, and the code around the test changed a lot. So some of the things were we needed an API client. Other people wanted to build on Sourcegraph. We added a lot more features. That means we added a lot more tests. That means our tests became slower to run, even slower than before. We added a lot more complex URL routes. So the way our URL structure works is if you want to go to a repository on Sourcegraph, it's actually sourcegraph.com/github.com/user/repo. And then you can even go to a function within a repository. So it gets very long and complicated. So putting the routes as strings in our tests was a big pain. We also wanted to access the data store directly. In the previous version that I just showed, our API handlers would hit the database directly. They'd issue the SQL. And there was no separation between the HTTP handler part of the API and the part that interacted with the database. We needed to separate those because our back-end stuff wanted to hit the database directly. And also, people who build on top of Sourcegraph using our API client, we want them to get the benefit of all the testing infrastructure we've made. Because one pain we had was we hit the GitHub API a lot, and it would be really nice if we could mock that in our API client tests that hit the GitHub API, but we can't. So we want to make it so other people who use our service can do that.
Yep. The mocking directly accessing the database, what was the rationale for that again? Can you go into more depth?
Yeah, the question.
You have a PC, you should be API if you're also getting the database directly.
Yeah, so the question was, can you go into more depth about why we hit the database in our API handlers? Is that right?
In your, basically high-level tests, in the example you had in your HTTP API, is that what you're trying to put the database into? Also hit the database here?
We didn't want to hit, so the question was, well, let me clarify. So here, the only database interaction we had in the test code was putting data into the database as fixtures. And then when you'd make an API request to our HTTP API, it would go and issue SQL queries, get all the repositories or something like that. And that's not good for two reasons. One, in the test code itself, we're having to do all this database interaction, which is slow. And two, in our API, we don't separate the part that issues the SQL and deals with the data store from the part that interacts with the HTTP request and determines what to do and what to respond with based on the data. Did that answer the question?
So you're kind of splitting out one very in-depth feature test into chunks.
Right.
Yeah, so this code, I just want to make it clear, this is bad. It worked, but it's bad. So I'll jump ahead to the end, and then I'll go through how we achieved all the goals we wanted. So now we have these 3 layers, and our tests are comprehensive, so they're going to test all of those layers. But at the same time, they're not repetitive. So even though a lot of the things that we want to test in each layer are the same, we don't have a lot of repeated code and a lot of error-prone code. So it's very DRY. Our tests are quick to execute because they don't hit the DB, and they're isolated so we can parallelize them. The things they test are also isolated. So when we're testing the API HTTP handlers, we're not testing the rest of the stack as we were before, like I was just saying. And also, people who build on our app can use our testing infrastructure to get these same benefits in their code. So here is the high-level overview of what we did and how we got from V0 to what we have now, which is where our tests are pretty solid, but I hope that all of you can criticize what we have and help us improve them further. So I'll start out with building an HTTP API client. So in the old world, the only API consumer was this AngularJS front end that we had, and it was in JavaScript. We didn't do any kind of code sharing between the Go backend that implemented the API and the JavaScript front end. Now we have multiple API consumers, some people using it. We have multiple services of our own that use it, so it's more of a microservice architecture. And the code is open source. You can check it out. It's based on Go GitHub. And here's a quick just overview of what one of the API client methods looks like. This is to get a repository. A repository is on Sourcegraph, and getting it will tell you the name, some stats about it, how many users it has. So the basic overview is, you call new client to get a client, and then you can call new client.repositories.get. That will trigger this method. And this method will construct the URL, issue an HTTP request with get, and then just parse the JSON and return it. So that is the basic overview. Again, you can check all this code out in the main repository, Go Sourcegraph. So we get 2 nice things out of this. The quick win, let me get my iTunes off. There. So now that we have this API client in Go, there are 2 nice things we get. One of the things is a quick win, which is in our tests that previously also issued HTTP requests to get the data, we can just use our API client, because that does the same thing the tests were doing. So now instead of having all this messy test code, we can make a really good API client and use that in our tests. That's awesome. A more involved win that this gives us is it gives us the opportunity to take the interfaces that this API client implements. For example, the repository service with get, get, list, search, all the actions we'd want to take on repositories. And not just for repositories, but for all the other nouns in our system too. So that is an interface. We also have this data store that does the same exact actions on the same exact nouns, but instead of issuing an HTTP request, it issues SQL. And it turns out that the data store and the API client both implement the same interface. Both have a get repository method. Both have a list repository method. And so the next thing we did was we took these 2 implementations. One hit the database and one hit our API, and we unified the interfaces in Go that they implement. Now, Go has nice interfaces, but this applies to any language. It's just about unifying the external API of your API client and your data store. So if you recall that get method on repositories on the API client, we have something really similar on the data store. And this is just like the code snippet that I showed for the client. You have new data store. It gets a database handle. Given a data store, you can just call datastore.repositories.get, and you'll get the repository back. So that's nice because previously we had this whole set of code that interacted with the DB and this whole set of code that interacted with our API. But now they implement the same interface and they have the same behavior. So it's much easier to understand what our code does. It also means that by necessity we're forced to share the same data types that we used for a repository and for the other nouns and all the parameter structs. When you're listing repositories, what do you want to sort by? What do you want to filter by? So all those things are now shared between our data store and API client. And another win that I'll cover in just a few minutes is because we now have this common set of interfaces, we can make really good mocks for those and use them throughout the system, everywhere else that we test. Any questions so far? All right. So one other thing I want to point out about how we made our web app easier to test is you saw that in our API client we are generating the URLs by string. So we had this line. And as I said, we have a complex route structure, and if we change how you get a repository, then it's going to break this. So we came up with a way to actually share the route definition and the routing so that, let me show an example. So yeah, we're sharing where we define the routes and where we actually attach them to handlers. You can do this in a lot of the Go routing packages. We use Gorilla Mux, and it works particularly well for this. And what this looks like is you have a function that will return the router, but this router doesn't have any handlers attached. It's like an abstract router. And you define your routes. I've only put one here for simplicity. And you name them so that they can be referred to later. And then in your server, what you can do is get a copy of the API router, attach the handlers. In this case, with this library, you call handler func. And then you just, using the standard Go HTTP handle, you just set that up. So the nice thing about that is you have this new API router function that returns the same router that the backend and the client will use. And then here's how you could change the API client to use the route definition you've already made instead of making its own with like sprintf. So here we just get a copy of that route and call URL on it, which is how in the library we're using you actually generate that URL. So that simplifies our test code a lot. And then the final thing which I mentioned is now that we have these set of unified interfaces that describe all the actions you can take on all the nouns in our system, we can make mocks for them and use them throughout. So previously, as I said, our API tests would test the entire stack. We didn't have any good separation because we didn't have good mocks. And now we can have separate tests for each, and we mock the components that we're not directly testing so that they run super quick. And this is the particular mock structure that we use. As far as I know, nobody else uses this. So we think it's good. It works for us. But for those of you who have done Go testing or who want to look into it, I'd love it if you take a look at this and let us know if there are any improvements to it. The basic idea is, in addition to the new client function in our API client, you can also get a new mock client. And that will let you, so that is a struct that just has fields, and you can assign the implementation, the mock implementation of any API method to these fields, and then this mock repo service will also implement that same unified repository interface. So here's what it looks like when you actually use it in a test. If you recall that really messy test code that I showed earlier for testing repositories Git, now it looks like this. So there's this global mock data store, and we'll just call .repo. Repo is actually a mock. That's the way we set it up in the setup function, which is not super relevant to this. And then we just put the implementation of the method, the mock implementation here. And this means that the thing we're testing will call that implementation instead of whatever else it would call. So things like this are actually a lot easier in dynamic languages like Ruby, but this is a pretty good way to achieve it in Go. And then what we're testing is the API client, and the API client, of course, hits the data store. And so, the code for API client repositories.get will eventually call the data store, and this is the method that actually gets called. So that's mocking in Go. That's how we do it. So yeah, those 4 things are how we got all the goals we wanted to out of testing. So we test all 3 of the layers in our system. We benefit a lot from the Go compiler to warn us if things are wrong and to help us with the refactoring. And tests run much faster. They literally run in a second, all of them. Most of that's probably process startup anyway. And yeah, for people who want to build on our API, they can use the same new mock client and actually essentially mock Sourcegraph for when they're running their own tests. So that's that. That's what I wanted to show. I'd love to hear criticism of what we've done, other things in similar things in other languages, and any other questions you have about this. So thanks. Yep.
What do your tests look like? Go all the way from the front end on the web, all the way to the database and back. Presumably you got a test suite that exercises the entire stack.
Yeah. Right now, the way we do that is a little bit informal. So the question was, how do we do our essentially like integration tests or end-to-end tests? And we just use like shell scripts to start up the server and just hit it for some expected behavior. We don't have like super formal tests. We do have a lot of instrumenting in our live app. The way we look at it is we're trying to bite off a really big problem, which is like analyzing all these languages and making this entire website that has a lot of the same functionality as GitHub, and we're just 4 people. So for now, we look at what are the highest priority issues based on what are people actually seeing in real life. That's worked well so far, but obviously it's not going to keep working forever.
Yeah. You mentioned unifying other interfaces. It doesn't seem like it sounds like that happened to work well for your particular application because it ended up that your API has a very similar interface to your database interactions. I don't really see how that necessarily relevant to simplifying your test suite, though. Do you feel like that's a prerequisite in order to create a simpler test suite in Go? Is to have unified interfaces between the layers?
So the question was, in our application, it looks like it turned out that we were able to unify the API client interface and the data store interface, but that might not be the case for every kind of program. And if that's not the case, then how would you do this? And is being able to unify them a prerequisite for getting these nice tests? It's not a prerequisite, but it makes it easy because then we can have one set of mocks. And then the different layers are essentially, we can think of them in the same way. So if we want to test this layer at the top, then we mock everything below, and those use the same interface. And so it turns out that the test code that we have actually looks really similar for each layer. So it does make it easier, and it was the progression that we had. But if you're not able to find that kind of similarity in your external API interface and your data store interface, then I think you'd have to do some things differently. But yeah, it's certainly not a prerequisite. I wanted to show what was our progression and how did we at each point improve our tests and reuse code to do that all around the system. Yep.
So I was curious about your tests, like you kind of building a search engine, the results, they can change a little bit and you probably still didn't make a mistake, it's probably still valid. How do you handle that in like your shell script that goes end to end? Does it say like these are exactly the results that appear? Does it say like these results are on the first page? Like what does that look like? Is it wishy-washy or is it?
Yeah, so the question is how do we test search given that search results, it's hard to say what exactly should be at the top, especially when there are a lot of complex things that go into relevance and it depends on all the other data in the system. The problem we have for search relevance is a little bit different from that of like Google. Exact matches are important. If you type in a function name, you want that exact thing, and that probably happens more often than Google. So we don't test search in that way right now. We test it as a system. We don't test search relevance. We just don't know how to yet, and it's not like super priority for us because the things that you see on the site are good enough. But as we do more with search relevance, we'll do a lot more there. Any other questions? Yep.
You kind of talk about your goal being, can I find somebody else who's already done this thing that I'm thinking of doing, right? But that does seem very much tied into the relevance question, right? Because if you already know the exact name of the function that you're looking up, right, then you're probably not wondering if somebody has done something literally doing.
Yeah, so the question is, if you know the name of the function that you want to call, then you probably already know how to do the things with that function. So there are two kinds of like search that we have. One of them is you find the function, and the other is you find an example. The workflow right now in Sourcegraph is pretty much the function or some keywords in the function name, and then given that, what are the examples of people using that? And also you can browse to the function without knowing it by name. But we don't do any kind of relevance for examples right now. So given some really common method, we just show all of the examples that are out there. That's something we want to improve on. But for right now, it's usually good enough to just really quickly see all of the examples. And you can scan that and see which ones are relevant right now. But we will improve that. Any other questions?
Yeah.
So, everybody else, but you do like how the code to find out if it's the same function, right? And then you match the exact function of names. Is that how it works? Or?
The search, yeah, so the question is how do we do the search? And to index it, we do analyze the code, we spit out all the definitions, and we understand, for this function, how many other callers are there. That's one of the inputs to our relevance. And it's not just an exact name match, but exact name matches are weighted pretty heavily.
I guess my question is, like, if someone is like renaming the function in the code, would like someone search results or?
The question was if someone renames a function in their code, if you use some kind of like meta programming to rename an existing method that you're calling, then we might be able to trace it. It depends on the type inference. But if you've made a fork of some library and you rename it, then if you search for that new name, you're going to find the version in your fork and not the versions that you forked from, essentially. But we do want to do a better job of tracking changes to functions when they're renamed, because that can give you a really good idea of like how has this function changed over time. You don't want it to just cut off the history if it's renamed.
Do you do any other testing of your Angular stuff other than this end-to-end shell scripting kind of stuff? Or do you use unit testing for factor?
Yeah, the question was, do we do any other testing of our Angular app? We switched from Angular, and now we're just generating the HTML on our server side. When we were using Angular, we did use the built-in E2E, and we did use Selenium. And now we don't have Selenium. We just test the HTML that our handlers return.
There's a lot of JavaScript in the site.
Yeah, the question was, is there a lot of JavaScript on the site? Turns out there's not a ton of JavaScript. It looks like a rich app, but it's actually generated a lot behind the scenes. The reason for that is search indexing by Google is really important to us, and having URLs that mean things is really important. And that's much easier if we do more of it on the server side than in the front end. All right. If anyone has any other questions, then we'll stick around for a little bit. And everyone who asks a question can come get a T-shirt. If we don't have enough, then we'll just mail one over here. So thanks.